So welcome everybody to Utar 2's EPSSCOM 2020 presentation. So in 3.0 and 4.0, we try to model the system in PSSE, and the voltage level are displayed with different colors. So the cable values are shown in the table, and we use 20 degrees Celsius because it gives a upper bound value, and we use 50 Hertz for the reactance because we assume that it's a Malaysian system, and for the capacitance, we will use it to calculate the susceptance. So the zero sequence and susceptance is modeled using the equations given, and the table summarizes the data for each of the cables. Next, for the transformers, we assume a vector group of DYN11, and they are specified in PSSE as shown. So PSSE does not convert the impedance to appropriate base 100 MVA, so it has to be done manually. Next, the NER resistors at each of the 132 kilovolt transformers have to be approximated, and one step towards that approximation is to assume that the impedance of my city and the industrial facility is 0. So according to Glover, the I fault is given, and since the two transformers are parallel, their equation is modified, and the zero sequence impedance is 0 due to a grounded Y neutral. Next, the I rated is calculated as follows, and from there we can derive inequality, and we find that the NER resistance is 18.1863. So without NER and with NER, the results are compared, and with NER we find that the short circuit current is below the 2099 rated ampere. So in 5.1, we try to audit the base case, and for the base case, all loads are assumed to have a power factor of 0.85, and according to the IEEE specification, the circuit breakers should not be loaded over 80% of the current rating, and this is why there is this I soft divided by 0.8, and the continuous ratings are summarized here. So next, the short time rating is approximated by doing IEC 60909 fault analysis in PSSE, and to determine the rating, we use a voltage factor of a maximum 1.1 pu, and the results are summarized here. And for the next part, we try to approximate the maximum allowed switchgear duration for each cable by using the following equation, and the results are summarized in the table. And finally, we try to audit the base case by considering the minimum voltage factor, and if we compare the results, they are as expected. And for the final part, we list down the underloaded buses, and there are no overloaded buses. So in 5.3, we try to reduce system losses using shunt capacitors at the MyCity network. So the loads are circled in red, and PSSE, we try to find the total real and reactive power. And based on the load duration curve given, we find that the total kWh is as follows, and we also calculate the annual demand cost and the annual total cost. Given the cost constraints, we try to place capacitor banks at each load to maximize power factor, and we calculate using those constraints to find the cost and the annual maintenance cost. And from there, we approximate that 3 months are required to pay off the capital cost. And for the second year and beyond, the savings are definitely enough to cover the annual maintenance cost. So in 5.4, we also try to reduce the loss by selecting open points. So in this section, we try to reconfigure the network by turning on and off switches. And for this particular analysis, we only turn off one branch. So by doing so, we can try to reduce network losses. So using ETAP, we try to approximate the total power loss by turning off each of the branch, and we find that cable 11 gives us the lowest power loss. Therefore, cable 7 is the most optimal configuration. In section 5.5, power factor correction at the industrial facility is achieved by placing capacitor banks, and we choose a 25 MVAr capacitor bank to lower the power factor, to increase the power factor from 0.86 to 0.985. And in section 5.6, we analyze the capacitor bank switching using PSCAP. So before doing that, we try to find the Thevenin impedance of the PMU33 kV bus using three-phase fault analysis in PSSP. This impedance is specified as the source resistance in transient analysis. So in PSCAT, we first we conduct an isolated bank where only one bank is connected to the bus and the bank is grounded. So the breaker is closed after 0.2 seconds, and theoretically the I peak and F peak should be as follows. And from the results, we find that the results are quite close to the theoretical value. And we also find that they are within the IEC switching requirements. When we conduct the ungrounded scenario, we find that the results are exactly the same. Next, we consider the back-to-back scenario where two or more banks are connected to the same bus. Conserve here means that the 25 MVR bank is split into two separate 12.5 MVR banks. So breaker 1 is closed at 0.15 seconds and breaker 2 is closed at 0.2 seconds. So from the results, the peak of both banks are obtained, and we find that this scenario reduces the peak current and doubles the frequency. However, it's still within the IEC limits, and the same results are obtained for ungrounded banks. Next, the inflated scenario means two separate 25 MVR banks are connected to the same bus, so the breaker configuration are still the same, and we find that the peak current is doubled and the frequency is maintained. They are also still within the IEC limits, and the same results are obtained for ungrounded banks. In 5.7, we analyzed the transient transformer energization at the two parallel 132 kV transformers. So the second windings are connected to 10 to the power 7 ohms to simulate the unloaded scenario. All circuit breakers are closed at the same time at 0.1 second when phase A's instantaneous voltage is 0 to maximize the inrush effect. So initially the bus voltage is 1.038, and then it sags to 1.03 and it stabilizes back to 1.038. And then according to the ENA, the rapid voltage change is basically a change in RMS voltage between two steady state conditions as defined by the ERP828. And we find that the change in the Vmax is 0.8%, and these results are within the ENA requirements. Due to technical issues, the effects of remnant flux cannot be modeled accurately in PSCAT. So as a countermeasure, we insert 200 ohms resistances at each circuit breaker, and the time delay for bypassing the pre-insertion resistor is set at 7 cycles, as suggested by Hu in 2011. So the results show an improved change in Vmax of 0.1%. Next, we consider the sympathetic scenario where one transformer is already energized and another transformer is connected to the bus. So in our context, TX1 is already energized and TX2 is connected to the bus. So from the result, we find that the change in Vmax actually decreases from 0.8 to 0.4. I'll pass the time to Arena Chin for 5.2, 5.8 and 5.9.
Moving on to 5.2, protection scheme for the industrial facility. The diagram shows the one-line diagram on ETAP of the industrial facility. So according to J. Duncan Glover, he states that the type of protection depends on the transformer rating. So in this case, the fuse are used for TX8 and TX10 since the transformer rating is less than 10 MVA. For the rest of the system, a combination of overcurrent relays and circuit breakers are used to protect the system. To demonstrate how the protection devices can protect the system from certain faults, I'll give some examples. So in this case, let's say there's a fault occurring on the line between substation 200 and the gas compressor. Circuit breaker 6 will open and circuit breaker 23 and 25 will act as secondary protection. So that means if circuit breaker 6 does not operate, circuit breaker 23 and 25 will open. Another example is, let's say there's a fault occurring at substation 210. The fuse will open and circuit breaker 23 and 25 will act as secondary protection. Next, if a fault occurs at cable 1, circuit breaker 22 and 23 will open to protect the rest of the system. It also isolates cable 1 from the rest of the system. Next, if the fault occurs at bus substation 200, circuit breaker 23 and 25 will open. Moving on, this table illustrates a summary of the expected operation of the circuit breakers according to the fault location. Next, in 5.8, we will talk about the protection relay coordination for industrial facility. In this case, there's two subsections, which is overcurrent relay coordination and relay coordination for earth fault. To summarize, there are these few steps in this flow chart to determine the relay coordination. So firstly, we have to analyze the type of power system. Next, we have to determine the current transformer ratio. Third, we have to find the pickup current. Fourth, we have to plot the graph of relay operating time against MPS. MPS is short for multiple pickup setting. It's also known as pickup setting multiplier. The IEC curve consists of 4 types of graphs, which is short time inverse, standard inverse, very inverse, and extremely inverse. After calculating the MPS of the relay, we can determine the time dial setting and the relay operating time from the IEC curve. This diagram shows the single line diagram between PMU to industrial facility. Next, we will analyze the overcurrent relay coordination. As stated just now, the first step is determining the CT ratio. Next, we have to calculate the pickup current. And the third step is we have to plot the graph. So there's 4 different types of graphs that we can refer to, which is the short time inverse, standard inverse, very inverse, and extremely inverse. Placing the graphs together, you notice that different standard has different characteristics in terms of the steepness of the graph. The last step is calculating the MPS, which is the ratio between short circuit current in CT secondary and the pickup setting. From the MPS, we can determine the TMS and relay operating time from the IEC curve. Similarly, we do the same for earth fault, but in this case, for earth fault, the current to be used must not exceed 20% of the unbalanced current. Using ETAP software and the star view, we can also plot the overcurrent relay coordination curve for phase and for earth fault. Next, this is a part of verification on the ETAP software. So in this case, if a fault occurs on cable 3, circuit breaker 24 and 25 is expected to open. But in this case, circuit breaker 6 and 24 operate because 24 is enough to clear the fault, while circuit breaker 6 detects fault current in the gas compressor. This is most likely because the impedance of the gas compressor is very low. Next, if a fault occurs at substation 210, fuse 2 is expected to open. Lastly, if a fault occurs on bus PMU 33 kV, circuit breaker 27 is expected to open. Moving on to 5.9, which is determining the direction of the directional overcurrent relay setting for MyCT ring circuit. In this table here, we assume that the arrow pointing upwards is reverse bias, downwards to represent forward, and arrows on both sides to represent non-directional. So by selecting these directions on the overcurrent relays, we are able to isolate the fault and allow the rest of the system to operate. So in this case, if fault occurs on cable 7, the fault current flows in these 2 directions, and relay 9 and 23 will operate to isolate cable 7. Next, if a fault occurs on cable 8, relay 12 and 24 will operate to isolate the fault at cable 8. What about fault occurring on bus? In this case, the relay 9 and relay 24 will operate to isolate the bus. So in this table, it basically summarizes the actions of every relay in regards to the fault at certain locations. Now I will allow Fong Qianyong to continue presenting his slide for 5.10.
So in 5.10, we investigate the arc flash hazard in the industrial facility. So based on the table, we just fill in the values in the Excel spreadsheet, and the values are derived from the IEEE specifications. For instance, since it's a high volt switchgear, we use a working distance of 910mm. And the equipment class 3 because it's a switchgear, and the protective device type is 0 because the model, the chosen circuit breaker model is not listed in the Excel spreadsheet. So the arc flash is calculated for maximum and the minimum 3-phase fault current, and the minimum is actually 0.85% of the maximum. We find that the arc flash energy for the maximum and minimum is actually within the 40 calories per cm square. Next, I'll pass the time to Diranza for 5.11.
So I'm Yanze. I'm presenting the off-grid photovoltaic system development. I give myself some aims, trying to make the design special a little bit. I want to make it applicable even in real world. So the way I do it is by assuming any possible losses, even if it's very minor, very small, I'll take it into calculation. And secondly, since the solar photovoltaic is very sensitive to many things in nature, so like suddenly there's too much power input or something like that, I will assume any worst case that could happen to the system, so that even if the worst thing happen, the system can still run. And this is the overall content of the report, and also how I do my arrangement, what comes first and what comes the last. So first of all, I calculate all the required loads, and then I select the equipments I needed for according to each of the loads. And lastly, I find which solar array is the most suitable, and then I calculate the area. Speaking of selection of components, there are some criteria I use to select the components, and the first one, which is the most important, is whether it's compatible with other equipments or not. As we all know, the system is not independent, they are all interconnected together, so I need to make sure all the voltage and current power, they are all compatible to each other. And secondly is the efficiency, because efficiency means money. If I can lower down if I can lower down the power loss, that means the overall cost can be better, can be lower. And thirdly, I'll see if there's any additional functionality, like some controllers that can be controlled with internet. Those are the least important. And lastly, the formula I use for the whole calculation is this. It calculates the watts needed to save from the solar panels, and this is the most important because there are some other calculations like how much power needed for inverters, for batteries. They are all derived from this. It includes the days of operation, as you can see, and the demand I needed for the loads. The GPSH means the daily sun hours, and these are the charge and discharge efficiencies. So it actually includes everything I needed. That's all. So now I'll pass it to Hao Dion.
I'm going to talk about applications that can constitute the smart grid. In terms of grid resilience targets to withstand the low probability and a high impact disturbance. The power system is deemed as critical infrastructure, and any damage to it directly inflicts on the country's economy, since other critical infrastructures depend on electrical power for its operation. For demand-side management system, users are encouraged to participate in energy management. Thus, with the knowledge of the user and the latest technology of renewable energy sources, many users are equipped with rooftop solar panels. Renewable energy sources are reducing the reliance on the traditional power system and decrease the supply pressure of power grid. However, the implementation of DSM in the smart grid deals with several challenges such as security and privacy, tariff regulation, and more. For Internet of Things, with the technology of it, a smart meter will enable you to manage your electricity better by monitoring what you are using. Nowadays, PNB is aggressively installing smart meters across Peninsular Malaysia. However, cyber attack may involve in any cases.
Okay, well, that's all for our presentation. Thank you for listening.